Hello everybody, and welcome to our next installment of the Fundamental Theorem of Calculus. In our last video, we talked about the Fundamental Theorem of Calculus Part 2, which tells us how to evaluate a definite integral. And interestingly, you need to know how to evaluate a definite integral if you want to understand the Fundamental Theorem of Calculus Part 1, which is what we'll be talking about today. So, the first thing I would like you to do is take a moment and try to do this integral in front of you. Hopefully you're good to go. Notice that it is a t here. There's a reason for that. So when you integrate, be careful. Don't make the same mistake I did, and I had to go back and fix it, of putting an x here when you integrate. It's not an x. This is an integral taken on t, so when you get done, your expression should be in terms of t. So take a moment and do that integral. All right, so now that we've done that integral, we see we've got this is whose derivative this is, right? T squared plus 3t. If I take the derivative of that, I get t squared, 2t, 3t turns into a 3, and then there could have been a constant at the end. I don't know. All right, now, Fundamental Theorem of Calculus tells us how to handle something like this. So notice, same integral, but the only thing that happened is now we have limits of integration. So let's use the Fundamental Theorem Part 2 to evaluate this definite integral. All right, so and now we're going to evaluate a definite integral. We're going to take the generic indefinite integral that we did and do this evaluation from 2 to 5. Okay, so as you know from our last video, that in order to do that, all you have to do is plug in your upper limit, plug in your lower limit, and do a subtraction. Again, it's always upper limit minus lower limit. So we see here we plug in our 5x. Don't forget the parentheses because the 5 gets squared as well as the x. Times 3, and then I have 2 squared plus 3 times 2. And so if you simplify that out, you get a nice polynomial. You get 25x squared plus 15x minus 10, okay? Which I expect to get a nice solid answer, but interestingly here, my answer is in terms of x. So it's kind of important that you note here that this integral started in terms of t and ended in terms of x. And the reason for that is I plugged a limit in. One of my limits was in terms of x. Okay, and that's how the variable switch happened here. All right, so I did the derivative, or I'm sorry, I did my integral. I've got this polynomial here. Okay, so why does this matter? Okay. This is where the Fundamental Theorem of Calculus Part 1 comes in. Notice here that this is the same integral from before, except now they want us to take the derivative of it. And this should sound a little bit familiar to you because when we first started talking about the fundamental theorem, what we said was that integrals and derivatives are opposite operations, right? They undo one another. This is the magic of this. So if I want to do the derivative of this integral, I can start with the fact that I already evaluated this integral, right? I know what this integral is. It's 25x squared plus 15x minus 10. So if I take the derivative of that, I get 50x plus 15. We've been able to do that since like the first week of school. I have a problem though. This is making my wheels spin. Because we just said that if you take the derivative of an integral, those things undo one another, right? If I take a derivative and I take an integral, those things are supposed to undo each other, right? Like that's one of the first things we talked about. If I have x squared and I take its derivative, I get 2x. If I have 2x and I take its integral, I get x squared. Now, plus c, but nonetheless, I get x squared. I need you to notice that that is not happening here. Okay, I took this function, 2t plus 3, took its integral, and then took its derivative, and I did not land back on my same function. Take the tx piece out of it. Its variable is a variable in this case. Notice here, this is changed by a factor of 25. This is changed by a factor of 5. You can't even like take one whole factor out of it. Something's going on here because we know that derivatives and integrals undo each other. That's literally what the foundation of the fundamental theorem of calculus. So what we have to figure out is what's going on. Okay, so if you look in most calculus textbooks, This is how they present the fundamental theorem of calculus part 1, also known as the derivative of an integral. They say, and this is a whole lot to look at, but bear with me here and break it down. If you take a function h of t dt, the variable here is, I call this t a dummy variable. It doesn't really matter. They almost always use a t, but why it's a t, I don't know. Okay. I'm going to take this integral, and notice here that this integral is a definite integral, and it's going from a, which is a constant, up to x. And they say if you take this integral and you evaluate that, you get, and then you take the derivative of that, look what you get back. The exact same function, right? In terms of x, but the exact same function. Now, that's what you say is true, but we just did an example and we saw that that wasn't true, right? And the reason in our example it wasn't true is because that is not the whole story. Okay? You may have noticed that in our example, our lower limit was a 2, that's fine, but our upper limit wasn't an x. It was a 5x. Now, you also may have noticed that the numbers that it was off by were 5 and 25. Here's the thing. This definition forgot about the baby. This is a very, very special case of what we know the true story, the whole true story is. In the fundamental theorem of calculus, this technically right here is true. Okay? But again, this is not the whole story. Now, I'm going to animate the whole story in below, and I'm just going to say in advance that it looks really, really complicated. On the next slide, I have it in terms of like hearts and clouds or something, and you might like it a lot better. Right? But let's just look at it in its full crazy form. Right? Okay, so here this is. I have the derivative of an integral. Notice my integral is the same, h of t dt. The only difference here is instead of just a constant on the bottom, we're allowing for any function. Now, this could be a constant, right? But it could also be an x or an x squared or a sine x or whatever. Okay. And on top, instead of just an x, like up here, we're allowing again for any function at all. It could be a 2, it could be a 27x, it could be a cosine x, it could be an e to the x, it doesn't matter. Okay. Now here's what we know. If we integrate this function, we might get what they call capital H of t, right? And then we would evaluate it, right? We would plug in its lower limit and its upper limit, and we would subtract. And that's what you see here. Okay. This is upper limit minus lower limit. But you may notice here these aren't capital H's, they're lowercase h's. Well, that's because we're also taking the derivative. So the derivative, when I do the integral, it becomes capital H. When I then take the derivative, boom, I'm back to lowercase h. And this is where the baby comes in. If you take the integral, you plugged in g of x and f of x. When you then take the derivative of that, the things that you plugged in get chain ruled. Right? So in other words, if you're going to plug in g of x when you do your integral, then when you take your derivative, there's going to be a g prime of x right here. And if you're going to plug in f of x to your integral, then when you take your derivative, there's going to be a chain rule piece here. There's going to be an f prime of x here. So this is the whole story. And look what this special case does. Look how this special case simplifies things. Your lower limit is a constant, right? So that makes this f of x right here just a number. Well, when you do that, what happens when you take the derivative of a number? 0. This whole chunk goes away. Okay. On the upper limit, they have just an x. Well, if all you're going to have is an x, then this piece would just be an x, right? And the chain rule piece would just be a 1. So you end up with just h of x. So it looks super simple. But the truth is, if you have anything other than a constant here and an x, just an x, on the top, there's more to the story than this. And this is what we have to know for sure. This is a very generic, yeah, the derivative and the integral undo each other, right? But this right here, that's the whole truth. All right, so let's take a look at this in a little bit of simpler terms. Oh, smiley faces. Okay, so all I did here was take the definition and I put clouds and smiley faces over top of f of x's and g of x's, okay? But it makes it look a little better. So once again, here I have h of t, and I'm integrating it from smiley face to cloud, and then I'm taking the derivative of it. Okay, so if you want to think of it like this, and say, okay, I'll worry about this derivative here in a minute. I'm going to take the integral of lowercase h of t from smiley face to cloud. That's going to be capital H of t from smiley face to cloud. Whoops, sorry, I didn't mean to draw an equal sign, sorry. That means I'm going to be taking the derivative of h of cloud minus h of smiley face, capital. Right? So when I actually do that, look what happens. The derivative of capital H goes back to lowercase h. But if you take the derivative of h of cloud, you have to tack on cloud prime. That's this piece. Then I'm going to subtract. I take the derivative of capital H of smiley face. I get lowercase h of smiley face. Chain rule. I almost drew a cloud. Smiley face prime. And that's this part. Okay. It is literally evaluating a definite integral, upper minus lower, with keeping the chain rule in mind, not forgetting the baby. Because in this case, what you're doing in one fell swoop is both a derivative and an integral. So you have to do the chain rule piece of a derivative and also the upper minus lower part of the integral. It's two operations in one. And when you do both of those operations in calculus, we know that you're going to come back. This function right here won't change at all because I did the derivative and the integral and they just undo one another. Okay, so in some words, let's mark this thing up a little bit. What you're going to do when you get a derivative of an integral like this is you're going to plug in your upper limit to the function that's sitting in front of you and then chain rule. Then you're going to subtract, plug in your lower limit to the function that was sitting here, and chain rule again. Plug it in, chain rule, plug it in, chain rule, subtract. Again, all we're doing is putting in our upper limit minus putting in our lower limit, and then remembering that it's a derivative of an integral. Since I took a derivative, I better have my chain rule pieces here. Okay. I'm saying this over and over and over again because every year when we talk about this, everybody says, yep, makes sense, Britton. Yep, this is easy. Yep. And then the next day I give them a problem and they forget to chain rule or something, or I find myself standing over top of people that are doing problems going, fundamental theorem of calculus. For some reason, this is a really easy thing for people to forget. It's like it goes in and everybody goes, yeah, that's fine, cool, makes sense. And then right back out again. So we're going to do a lot of practice with this because I probably don't have to tell you that this is a very popular topic on the AP exam. It is, after all, called the fundamental theorem of calculus. Okay, so I want to show you how they come at us with this. This first example is way too easy. AP would never, ever let us get away with something like this, and I will show you why. Because in order to do this problem, you don't have to know the fundamental theorem of calculus. In order to do this problem, I could just do the integral and then take its derivative, right? I could say, all right, well, let me just figure out what h of x is. You want h prime of x? Okay. Well, h of x is the integral of sine t from 3x to 6x. So let me evaluate that. Let's see, whose derivative is this? Derivative of sine. Oh, the derivative of cosine is negative sine, so this must be negative cosine of t. And then again, it's evaluated from 3 to 6x. So if I'm evaluating this integral, that would be negative cosine of 6x minus negative cosine of 3x. So I'm going to write plus cosine of 3x. right? That's h of x. H of x is defined as this integral. The question is, what's h prime of x? So I say, okay, well, h prime of x is just the derivative of this, right? Well, the derivative of negative cosine is negative sine, so the derivative of negative cosine is sine 6x, but oh, I have to chain rule, times 6. Okay, plus the derivative of cosine, which is negative sine 3x, but oh, I have to chain rule. So I took my integral of sine, upper limit minus lower limit, and then I took my derivative. But that was all unnecessary because I have the fundamental theorem of calculus. I could have just said, oh, hold on. You're defining a function as an integral and you're asking me for its derivative. Well, I don't need to do anything then, right? If you want the derivative of the integral, the function itself isn't going to change at all. If you take the integral of a sine and then you take its derivative, you end up with sine again. So all I have to do is do the upper minus lower thing. So sine 6x minus sine 3x. And oh, that's right, we're doing the derivative, so you better darn chain rule. So times 6 here, times 3 here. And darn it if we didn't get the same exact answer. But like I said, AP isn't going to let us get away with this, right? They want to make sure that you have to use this technique. So they are not going to give you something that you're able to integrate. They don't want you to do this. What I did here in purple, they don't want you to do that. So this is one of those cases where I said they're going to give you an integral you can't do. And what you're supposed to realize is, wait a minute, I can't do this integral, so they must want me to do something else. This is one of the things they want you to do. They want you to apply the fundamental theorem of calculus. Okay, so let's take a look at another one. Okay. We don't yet know how to do the integral of tangent. We will very soon, but right now we don't. I don't exactly know whose derivative that is. I don't care though, because look what I'm doing here. I'm taking the derivative of an integral. These two operations cancel each other out. So if I take the integral of tangent and then turn around and take its derivative, I know what I'm getting back. I'm getting tangent back. So all I have to do to evaluate this is do my integral, upper minus lower, and my derivative chain rule piece. Right? So this is going to be the tangent of 4x squared, notice I'm leaving space, minus tangent 2x, so upper minus lower, and then chain rule. The derivative of 4x squared is 8x, the derivative of 2x is 2, and we're done. Pencil drop. That's it. Now you can imagine that if you do not know the fundamental theorem of calculus, one might spend a very long time trying to integrate the tangent, plugging in these upper limits, then taking a derivative just to run into the same answer. One of the problems people run into on the AP is time. Okay? If you take too much time on a problem that should take 30 seconds, you're going to run out of time elsewhere. And they know that, right? So they know this is a 30-second problem if you know the fundamental theorem of calculus. They're going to make sure you know it. Okay. All right. Again, another situation where you better darn well realize this is an integral we can't do. And this is one we will not be able to do. Okay. But when you're sitting at the AP, you're going to say, oh, please. I see two really huge hints right here that something's going on. The first hint that I have is I have a function defined as an integral. Anytime you have a function defined as an integral, they're probably going to come at you with a fundamental theorem problem. Right? The next thing I notice here is that this is an integral. Well, you don't notice it yet, but I do. This is an integral I can't do. So you're going to be sitting at the AP and you're going to say, wait a minute, I don't know how to do that integral. And I am confident enough in my integral taking abilities to know that it's not because I don't know what I'm doing. It's because that's not an integral I'm supposed to know how to do. Add to the fact that I have a function here that is defined as an integral. I'm pretty sure I have a fundamental theorem problem. So I go look, and sure enough, oh look, the very function that they defined as an integral, they want me to take the derivative of it. Come on. Okay, so if I take a derivative in an integral, I know I'm going to get my original function back. So this is going to end up looking like the sine of upper limit squared minus the sine of lower limit squared. So 9x to the fourth. And I can't forget my chain rule pieces. Okay. Now, don't doubt yourself here. People doubt themselves here all the time. The derivative of what you plugged in here, the 5, is 0. The derivative of 5 is 0. That wipes this whole chunk out. The derivative of what you plugged in over here, 3x squared, is 6x. Note I took the derivative of what I plugged in, not its squared form. So upper limit minus lower limit. Function stays the same. Upper minus lower, you tack on, you chain rule the derivative of what you plugged in. If what you plugged in was a constant, its derivative is going to be 0 and it's going to kill that whole piece. That's fine. Here's my answer. Negative 6x sine 9x to the fourth. That is the derivative of this integral. Again, the derivative in the integral, I'm getting my same function back. Upper limit minus lower limit, chain rule. Okay, let's do one more. I picked a crazy function on purpose because, again, we have no prayer of doing this. It has crazy limits of integration. But the reason I wanted to choose one like this is because I want you to notice that the t shows up in more than one spot, right? It's here, it's here, it's here. So when we do our plugins, I'm going to be plugging in these limits of integration 3 times. But I'm only going to chain rule once. Okay, so watch this. Again, derivative of integral, we know we're getting the same function back. I just have to do upper minus lower. So my first one is going to be tangent cubed of t. So tangent cubed of 7x cubed, and then plus 7x cubed squared e to the 7x cubed. So I plug in 7x cubed to this thing. Tangent cubed of that squared, e to that. And then to that whole thing, chain rule. I'm going to do the same thing with my 6x. Let's plug it in. Tangent cubed 6x plus 6x squared e to the 6x, and then multiply that whole thing by the derivative of what we plugged in, 6. Again, it's the same exact thing. It looks a lot more complicated. Notice my function stayed the same. Tangent of something, or tangent cubed of something, that thing squared, e to that thing. I plugged in my upper limit in all 3 spots. I plugged in my lower limit at all 3 spots. I chain rolled. Derivative of 7x cubed, 21x squared. Derivative of 6x is 6. And we're done. Okay. Notice here that I put brackets around the whole thing. Those have to be there, because if they're not, this 21x squared doesn't apply to all this. So it's just kind of the mechanics of it. I've seen kids, when as soon as they see this, they go like this. Because they know they're going to forget to chain rule, right? So they're like, all right, I'll get to this in a minute. Upper limit, chain rule, lower limit, chain rule. So before they get into the throes of plugging it in here, they write this so that they don't forget to chain rule. I think that is a great idea. I'm going to end this video with one more thought. One thing you should never, ever, ever do, and I addressed this in a video the other day, but again, I see it happen all the time. People start to walk away from this, and before they walk away, they go, oh crap, I did an integral. And they write plus c at the end. No! Right? Yeah, you did do an integral. And I agree. When you do an integral, you're supposed to write plus c. But 2 things. This is a definite integral. So the plus c canceled. Layer that on top of the fact that you took your definite integral and took the derivative of it. So if there was a constant at the end, it's gone now. So writing a plus c at the end of this, oh man. Its layers are wrong. But people get panicked and they're like, oh crap, plus c. Don't do that. You only want a plus c at the end of an indefinite integral. Anytime there were limits of integration, there should not be a plus c there. Okay, so we are going to look at the different ways that AP throws this at us on Monday, or the next time I see you, I guess. Because sometimes they give them to us straight like this, and sometimes they kind of play with this theorem a little bit and make us use it. But we will take a look at that next class. I will see you soon. Have a lovely day.